All right, so today we are diving deep into something you can't see, you can't feel, but is one of the most powerful processes in the universe, radioactivity.
It's a weird thought, right? But for a lot of atoms out there, instability is just their natural state of being. They're built to break down. And this fundamental process, where an atomic nucleus just spontaneously decomposes to become something else, well, that's what we call radioactive decay. Okay, so let's get right into it. To understand what's happening, we have to start at the very, very tiny heart of the matter, the atomic nucleus itself.
So, at its core, radioactivity is basically an atomic balancing act. You see, when a nucleus has way too much energy, or just an unstable mix of its protons and neutrons, it just can't hold itself together anymore. To get stable, it has to change. So it spontaneously ejects particles and energy, and in the process, it often transforms into a completely different element.
Now, when these nuclei decay, they spit out radiation. Scientists figured out there are three main types, and honestly, the best way to get a handle on them is to think of them as three characters, each with their own unique superpower.
First up, you've got the alpha particle. This is the heavyweight, the bruiser of the group. Because it's so big and chunky, it's like a tiny bulldozer on a molecular level. It causes a ton of damage to whatever it smacks into. But that same size means it gets tired fast. It can be stopped by something as thin as a single sheet of paper, or even just the outer layer of your skin. Next in the lineup is the beta particle. Think of this one as a super fast electron. It's about 8,000 times smaller than an alpha particle, so it's way more nimble. It can get a lot further, zipping right through paper and skin like they're not even there. You're going to need something like a thin sheet of aluminum to stop this one.
And finally, we have the gamma ray. Now this one is a whole different beast. It isn't even a particle. It's just a wave of pure, high-octane energy. This is the ghost of the trio. No mass, no charge, which makes it incredibly hard to stop. It'll pass right through a person. To shield against gamma rays, you need several inches of something really dense, like lead.
So take a look at this. What's so fascinating here is the trade-off it lays out so clearly. You see that inverse relationship? The more mass something has, like the alpha particle, the more damage it does when it hits, that's its ionizing power, but the less it can actually penetrate. So the alpha particle is like a sledgehammer that can't get through the door, while the gamma ray is like a ghost that just passes right through the walls.
Okay, so that's all the theory, but how does this stuff actually play out in the real world? Well, to really see it in action, let's turn to two of the most infamous nuclear events in human history.
Both Chernobyl and Fukushima were rated as level 7 accidents. That's the absolute highest, most severe category there is. But here's the twist. Even with that same rating, the physical form of their radioactive fallout was completely different, and that difference created two vastly different environmental problems. To really wrap our heads around this crucial difference, we need to zoom way, way in, down to the microscopic particles that carried the most dangerous long-term radioactive material, a substance called cesium.
You know, after the Fukushima disaster, scientists were analyzing the fallout, and they made this pretty startling discovery. When they looked at that dangerous radioactive cesium, they found that in some areas, this number was the absolute key to understanding what was happening to the environment.
Just let that sink in for a second. The vast majority of this dangerous stuff wasn't some fine dust just blanketing the landscape. No, it was physically locked inside microscopic beads of glass that formed from molten concrete and reactor parts. This discovery was a total game changer.
So here's the bottom line. Chernobyl's fallout was made of these little fuel particles. Think of them like slow dissolving tablets that gradually release their radioactivity into the water and the ecosystem. But Fukushima's fallout was mostly these glassy particles, which are basically tiny sealed containers that don't dissolve. This made the cesium way less mobile and a lot harder for plants and animals to absorb, but it also meant it would stick around in the environment for a much, much longer time.
Okay, so this all sounds incredibly dangerous and persistent, right? So what do we do about it? How do we possibly manage this kind of waste? Well, the answer is surprisingly elegant. We actually use the very nature of radioactivity against itself.
And that's the beautiful part. Every single radioactive element decays at a perfectly predictable rate. We call it its half-life, and this means we can calculate, with incredible precision, exactly how long it's going to take for a dangerous substance to break down into something stable and harmless. We just have to be patient and let physics do its thing.
And that predictability is what makes the primary method for dealing with a lot of radioactive waste possible. It's called decay and storage, and it's as simple as it sounds. First, you secure the material in a shielded container, like a lead-lined box. Step 2, you just wait. You store it securely and let nature's clock do all the work. And finally, after a calculated amount of time, the material just isn't radioactive anymore, and you can dispose of it like any normal waste.
So really, when you get down to it, understanding this fundamental science, from the way a single tiny particle behaves all the way up to the fallout from a major disaster, is what allows us to turn what seems like a permanent hazard into a manageable problem. It's all governed by this unchangeable law of physics, a clock that's always ticking down toward a safe and stable end.